If you take two metal plates and place a material that does not conduct electricity, that is, a dielectric between them, you get a regular capacitor. Let's take a look at how it works. Before that, it's worth noting that the metal plates have an equal number of positively and negatively charged particles. In other words, the plates have a neutral charge. If you connect a power source to the capacitor, electrons will accumulate on one of the plates under the influence of the electric field. These electrons will begin to repel the electrons on the neighboring plate, while the positively charged particles left on the second plate will attract the negatively charged electrons on the first plate. Here, it also becomes clear that the number of electrons added to the left plate is equal to the number of electrons that have left the right plate. But as the number of electrons on the left plate increases, they will repel the incoming electrons. Therefore, it will become increasingly difficult for the power source to add additional electrons. Now, a total negative charge has accumulated on the left plate, while the right plate has an equal but opposite total positive charge. An electric field is created between these charges, which holds the charges in place. If the capacitor is disconnected from the battery, it can store the charge for a long time. Thus, in order to charge a capacitor, some work must be done. When charging a capacitor, its charge is formed by transferring charged particles from one plate to the other under the influence of an external energy source. Then, if you connect a light bulb to the capacitor, the accumulated electrons from the right plate will begin to move to the left plate until both plates become electrically neutral and the total charge on each plate becomes zero. That is, the previously separated charges now reunite, and the electric forces perform the same amount of work as was done when charging the capacitor. Thus, a charged capacitor possesses a reserve of potential energy equal to the work that was spent to charge it. Simply put, by charging a capacitor, we create an electric field inside it. When the capacitor is discharged, this field disappears. The work done by the energy source was used to create the field, and the work performed during the discharge of the capacitor is obtained due to the disappearance of this field. Consequently, it is important to note that any electric field contains within itself a significant and measurable reservoir of potential energy, which is released when this field eventually dissipates or vanishes. By the way, if we double the area of the plate, we will be able to push twice as many electrons onto the first plate and also remove twice as many electrons from the second plate. At the same time, we won't even need to increase the voltage of the power source. In this way, we have increased the capacitance of the capacitor. But what role does the dielectric play in all of this? As you know, a dielectric does not conduct current, but at the same time it still responds to an electric field, although not in the same way as a conductor does. The point is that in the molecules of a dielectric, the charge carriers are distributed unevenly. For example, one part of a molecule may have a negative charge, while another part has a positive charge, but the molecule as a whole is electrically neutral. In the absence of an external field, the molecules of a dielectric are randomly oriented, and the total electric charge of the dielectric is zero. However, when an external field appears, for example, if we place the dielectric between the plates of a capacitor, the forces of the field tend to orient the molecules in the direction of the field, causing the molecules to rotate and align themselves with the field. Thus, the negative charges turn toward the positively charged plate, while the positive charges turn in the opposite direction. As the molecules rotate, the neighboring charges in the dielectric mutually compensate each other. However, uncompensated charges appear on the outer surfaces of the dielectric. These charges create their own field, the intensity of which is directed opposite to the intensity of the external field. That is, on the left we have a plus and on the right we get a minus. This phenomenon is called dielectric polarization, from the word field. The resulting field begins to attract more electrons to the first plate and repel electrons from the second plate. So thanks to the presence of the dielectric, at the same voltage we can charge the capacitor more and increase its capacitance. At the same time, when we talk about capacitance, we mean a quantity that characterizes the ability of a capacitor to store charge. That is, the greater the capacitance of the capacitor, the larger the amount of charge it can store. In turn, the value of this charge is measured in farads. In reality, a farad is a very large unit of capacitance, and in practice, capacitors most often have their capacitance measured in microfarads, nanofarads, and picofarads.